Hello. Welcome to another section of data structure and algorithms. Today we do double and circular linked lists. And typically for any university curriculum, in the linked list syllabus, you would have double and circular linked list as the last part of the linked list syllabus. We have completed single linked list. We are right now into double linked list and circular linked list, and that would complete our linked list syllabus. Now, what do we cover today? We cover double linked list, which is the operations, the algorithms, the complexities. We cover the same thing on the circular linked list. So there are two linked lists that we'll cover today, both the double and the circular linked lists. We'll also understand the differences of it. And then, of course, we'll go through all the common questions that may be asked in terms of both these topics. Now, let's talk about linked list in a sense from, let's take a graduation step from a single linked list to a double linked list. Now what we are seeing on the screen is basically the two linked lists that we are discussing today, which is single linked list and how do we graduate into a double linked list for it. Now in order to ease off this diagram or what it wants to say, I hope all of you are aware of this part of this story, which is the head pointing to the first node of a single linked list, the first node pointing to the next node of a single linked list, the next node pointing to the next node, and so on and so forth until the last node points to null. I hope that is clear. If not, please see the last lecture on the single linked list that we have already covered. So this is what we have covered. Now what we are trying to cover today is what is a double linked list and how is it going to be different from a single linked list. Now if you see that the problems with a single linked list, if I take a single linked list like this and if I attach the relevant nodes to it, then what we will see is that, let's say if this is attached here and here, let's say this is at 100 address, this is at 200, and this is at 300, and we have a head pointer which is actually pointing to the 100 address. That means it is pointing here, and that's your linked list. And we have a null here, we have 200 here, we have 300 here, and that is how the linked list is linked, right? This is something that we already know. Now what will happen is that if you think about the fact that you are somewhere here and you want to understand what was your previous node, you can't. You'll again have to go back to head, and head will have to take you here to come back to the previous node, right? So that's the disadvantage. A linked list, single linked list, is always forward looking. So you can only go and see front or the next node, not the previous node, from your current node, and that's where the double linked list comes in. Can double linked list help me to see the previous node? Of course yes, and that's why we are studying it, right? So let us see if double linked list can help me study the previous node. So if I have another pointer on the left, another pointer on the left, another pointer on the left, right, then we actually have created something which is a double linked list. Now this should point to the previous node. Let's say this particular element should point to the previous node. What is the previous node here? The previous node is the first element. The previous node has to be null, right? So what do? We just put null here. And what is the previous element to 200? Previous element to 200 is this element which is at 100. So we will put 100 here. And what is the previous element to 300? It is 200. So we will put 200 here. And that's it. You have your double linked list. So what does a double linked list do? It creates this arrow and this arrow, and that is what is depicted here, right? So that is the depiction that is here. Since it doesn't have the addresses to make you understand, I redrew the diagram, and there you go. You have a double linked list which actually talks about both way propagation from any point in the chain, right? So if you are at 200, you have reached this node, you can go this side, or you can go, you have somehow reached this node, you can go this side or you can go this side, right? And that is the beauty of double linked list, which was not possible in a single linked list. So what do you need from a data structure standpoint? You need this, right? So of course you would need the data, which is the payload, and the next pointer. This we know from our linked list days, right? In addition, I told you that we have to actually introduce one more element, which is the previous, this element, right? And that is what you do with the struct node star pref, same as star next, same syntax. All you are doing is making a placeholder for the previous pointer. That's all you are doing. And you of course have your head equal to null, which is the starting point of a linked list. There are no nodes. If there are no nodes, what will happen? Star head will not have anything to point to. So it will also have null. So I don't have any linked list here. I don't have this. I don't have this. I don't have this. It's an empty list. So it will be null, right? So that's what either it will be an empty list to start with. We of course start with an empty list, right? So that's why the star head equal to null. Now in terms of operations, if you see, because we have a forward as well as a backward propagation, we will actually have 3 operations of insert, which is that we can now insert at the beginning, which was anyway possible with a single linked list. Insert at end was also possible with a single linked list. Insert after was also possible with a single linked list. But all these will now change in terms of complexities and will change in terms of the way we do it, because we now have a previous pointer to help us. And likewise for delete from beginning, delete from end, and delete by value, right? So this is what we will see from a operation standpoint for a double linked list. The traverse forward and traverse backward, again, traverse forward is there, traverse backward was not there for a double linked list, or a single linked list rather, my bad. For a single linked list, traverse backward was not there. You didn't have the previous pointer. Now you have the previous pointer, so traverse backward will be there. And of course, we'll also wrap it up with a search functionality operation in order to check this. Now, if we move forward, let us start with the first operation, which is the insert at beginning. Insert at beginning, and for us, for a simplification standpoint, let us assume that this is our current outlook of the linked list that we have currently in place, right? So what we are trying to do, we are trying to insert a node at a beginning. Now what I have tried or attempted to do is, and you would find various ways in which you want to remember things, I have attempted to create a small steps for you, which is applicable to all the inserts. And if you remember these steps, you will remember the syntaxes also, or at least the basic algorithms also corresponding to these steps. And these are the steps that you will do for all the insert operations. And we will see that for all the insert operations, I've given you the same set of steps. And for all the delete operations, I've also given you the same set of steps. So that way you can remember that yes, we may need to probably do these steps in order to make this operation currently feasible. So if I now come into the actual operation, so what do we need to do? What does it say? Create node, insert at beginning. To insert at beginning, first of all, you need a node, right? So let's create a node. So we will create a node like this, right? So the node is a double pointer node. So it will actually have 2 pointers, one at the left, one at the right, right? Now I have not put any value here. I have just created the node. What is the syntax to do that? You create a pointer. So we have a pointer called star new node. And then we ask malloc that malloc, please give us a memory. Malloc says, okay, how much memory do you need? I say size of struct node. That struct node we have already discussed in the previous slide. Go back a few minutes of this video, you will get to see what was the structure. It had a data, it had a next, and it has a previous. According to that data, whatever is the size will be returned by malloc into the new node. That means this memory will come into effect in the memory, right? And this memory has an address. So let's assume that this memory has an address of, let's say, 500, right? So if this memory has an address of 500, then what are we saying? It goes, that 500 goes into new node. So that 500 will go into new node, and we will point to the new node right now. Now the new node's previous is null, new or not even null. New node's previous is a junk value, and new node's next is also a junk value, and the data doesn't contain any data. So that is our create node step done, right? Next, what do we do? So create node step is these 2 steps, right? So this is my step 1. Now that's there. Now what do? We will accept the inputs because it is an insert, right? I need to know what to insert, right? So I will accept the input. The acceptance of the input comes here. This is our second step, right? So that is what we accepted. I hope there is nothing new here. What we are saying is that we'll accept the new input in the new node arrow data. So this is our data portion. We know that. So new node arrow data is the pointer. With the pointer, if you want to get into a structure, then you need to use the arrow syntax and not the dot syntax, which you are aware of from your C days, right? So that's where we have new node arrow data. Now, new node arrow data, I have put whatever came in. Let's say the user has given 10 as the input. So this 10 actually goes here. With this line, this 10 actually will go there. Next, what do we do? Next, we are saying initialize the node. When I say initialize the node, it means that can this node, without seeing left and right, can this node, based on the logic that we are trying to do, assume certain values for the next and the previous, any one of them or both of them. So again, let me repeat, without understanding where it is supposed to insert, that means without understanding its current, once it inserts, what is the left node, what is the right node, without going into that we will do later, right, at step number 5. That is where we will do that. But here we are just trying to say that forget about everything. Can we put a value in previous or next which will be the same always, considering insert at beginning? Yes, of course, because if we insert at beginning, what will be the previous pointer? It will always be null, right? So that is why we will say that the previous pointer will always be null, right? So that is what I mean by initialize node, right? And what will be the next pointer? Always the next pointer will be pointing to the head, right? So that the previous pointer is pointing here and the next pointer is pointing to where head is pointing. So I am going to have this point here. So that is where I will say this is equal to head, this line. So this is equal to head, and that is where what I will have is I will have this equal to 100. So now I have initialized my node, and this will be the same initialization that I will do for all insert at beginnings, and that's why this is perfectly valid, right? Now all I need to do is that, see what we have done, we have made this to point here, right? Now what we need to do is we will need to make this now in a such a way that we will traverse to the location that is supposed to be inserted, which is reach the insertion point. In our case, the reach insertion point is already done because we are doing it at the beginning. So there is no point of reaching the insertion point. Insertion point is the point where we are actually doing the head adjustment. So this head adjustment is where we are, where we have reached the insertion point. Now in that insertion point, what we will do is that if my head is not equal to null, then what will happen is that this head's previous, so see, now we are doing the adjust pointers. So we have reached the insertion point because there was nothing to do with respect to the insertion point in this code. So for all of you to understand, this step is not valid for the insert at beginning because the insertion point is already available to you in the form of head, right? For other cases, we will see as we go forward, this step will be valid, right? That's why I kept this step. So all we did is we created a node, we accepted the input, then we initialize the node like this. Now what is left to do? The left thing to do is, see, your head should point where your head should point to the new node, right? So this is what is left, isn't it? Because you're inserting at the beginning, your head should point to the new node that you have created. New node should point to the actual area where actual first or the initial first element which head was pointing to. So that we have already done. And of course, what you need to do is we will, and when you do this, right, this breaks. When you do this head pointer, so something can point only to one direction or one value, right? So if you are already pointing the head to 500, you cannot point the head to 100, right? So we are now changing this to 500. We will change this to 500 by this line. And also what we will do is, so this line gets wiped off because we did a 500. But this particular person now needs to be the second person in line. So its previous node should point to my new node. So I have to create a pointer adjustment for the previous node to point to the next node. How do I do that? I will have how do I go there? Our head was pointing to our head was originally pointing here, right? So head was originally pointing here. So what I will do, I will say head previous equal to new node. So what will that be? This is what we achieved, right? So head previous equal to new node. And then what will happen? Then very simply, I have to establish this, which is I have to establish this part, right? So these are the two things that we had to do for pointer adjustment. So I will say head equal to new node for that matter, right? So head equal to new node for that matter. So what does that create? That wipes off this link, that changes this to 500, that creates this particular head equal to new node pointer, and that also wipes off this null, and this node now becomes the second node. So the first node is where it should point, which is 500, right? So that is what this node will point to. And of course my first node should point to the second node, which is 100, which I have already done in this last step. So this is my step 5, where my adjustments are being done for that particular element, right? So we have done a create node, we have done an accept input, we have done an initialize is this, right? And then we have done a adjust pointers. Now I have explained this at length, and for the rest of all the operations that we see, I will go a bit fast. You can rewind this particular example to understand how I am correlating these 5 steps with the code as well as with the algorithm that I am drawing on the right? So let's move on with the next step. But then before that, what is the complexity? Complexity will be order of 1, because we know that we are only inserting at the beginning, and therefore we will not be encountering any loops, anything to reach our position where we want to insert. Hence we will directly insert our element by adjusting the pointers. Order is order of 1. Now we move on to the insert at end. The insert at end, if you see, if we take the same example, then my insert at end, again the same thing, 1 2 3 4 5, we will do the same thing, same set of steps. So first we will do the creation of node, and that creation of node is here, right? So that I am not explaining, we have already gone through that process. So now what do we have? We will have something which we called as new node, and this new node is a pointer which is pointing to an address, and this, let's say, is 500, our original example, and this address, this pointer is actually now holding this 500 as an address. So that is what we have done when we did this create node. Now accept input, again the same thing, this is where we accept the input, right? So we will say new node, the data of the new node. So new node was pointing here, this is my data portion. The data of the new node will be equal to, let's say we again take 10, right? So then we will put 10 here. Now all we are going to do is we are going to say that head, if the head is null. Now that's where okay, before going there, let us see the third step, which is the initialize the node. Now what do you think? Insert at end, right? Irrespective of where we are or whichever data set we are working with, whichever linked list we are working with, because this is insert at end and the element we are trying to insert will be inserted at end, there is only going to be one possibility for the next. It's going to be null, because it's going to fit at the end. So this node, right? So this node will fit at the end here. So if it fits at the end, this null will be invalid, whereas here we have to give it null. So the operation that we have to do, which is initialization of node, as I said, is irrespective of any kind of data that you have, it will always be the same. In this case, it will always be null. So please initialize that to null, right? So that is what we will do, and that is what we have done here. That is our third step, right? Next we have the reach insertion point and adjust pointers. Now here we will have to do it in 2 steps. because if we are talking of insertion at end, there are two cases basically that can happen. First case is my head is null. That means my head, which is this, is null, means I don't have any list at all, right? So in that case, what do I do? And our second case is what you see here, right? Which is basically the case where a head has something and there is a list, valid list. What do we do there? So again, for both the things, we'll have to repeat steps 4 and 5. So let us see how do we do. We reach the insertion point. If head is null, we are already at the insertion point. We don't need to reach anywhere, right? So what do? We will insert this element. See, this element has to be inserted here, right? And what do we therefore need to do? Our head needs to point to that element, right? So first thing that we will say is that head, you need to point to the new node, right? So that's what we will say. Head will point to the new node, right? So then this head therefore now becomes what? This head therefore now becomes 500. So it starts pointing to this particular node, right? Now what do we do? Now what we need to do is, since this now becomes the first nodes, its previous is still junk, right? And the previous needs to be null. So I will put the previous as null because there is no more items before this first node. So the first node's previous should be pointing to null. So what do? We say new node previous equal to null. That's all we do. And that's what we have done here. And this is your step 4, right? For the head equal to null kind of a situation, right? So what did we do? We reached the insertion point was not valid for the particular case because head was null. So we are already there. We just, what we did is we just adjusted the pointers, right? This is what we adjusted, the pointers. That's all we did, right? So this is for this particular head equal to null. Now let's assume that head is not null, right? So head has some value. So let me wipe this off and let me clear off so that you understand from the head not equal to null standpoint what is moving and what is not. Okay. So now what we need to do is case 2, our head is not null. So we have reverted back into the top example, right? So let me redraw this again so that we can make it from a clean slate. So we have a node. This node is what we are trying to insert, right? And we know that this will always be inserted at the end. So we have already gone through these steps 1, 2 and 3. 10 was inserted here, and this is how it looked like. The new node pointer was pointing here because this was at 500. So this is where we can probably think that this is how the situation will be after 3 steps of you trying to insert at end for a linked list that has a valid number of nodes, right? Not null. So now what do we do? We have to, so what are we talking of? We still have these 2 steps to go now, because this is something that we did for the head equal to null, which was a blank linked list. Now we are doing the repeating 4 and 5 again for the head not equal to null kind of a situation. So for a head not equal to null kind of a situation, what do? We will say reach insertion point. So head is not null. I have to insert at the end. What do? I loop through the taking head into a temporary variable or a pointer variable or any kind of variable. Basically don't disturb the head because head is very important. We will not disturb the head. If we change head goes on. We will not be able to access this list later on. So what do? We will take the head into a variable like a pointer here. And so we have taken head into the variable like a pointer. And once we have taken head into a variable, we are saying that we will take a loop where the pointers next is not null. That means this head is equal to the pointer. So we have a pointer here, star pointer, which is basically having 100. And this 100 is what we are now changing. So when we say pointer arrow next, so pointer is pointing here. So arrow next means what? This one, this element, right? So what is this? 200. So pointer arrow next means what? The next element, right? So or rather it points to the next element. It's not the next element, it points to the next element. Now if the pointer arrow next is null, we have already reached the end. So that's what we check. Pointer arrow next is not equal to null. Till the time it is not null, you do what? you will change the pointer to the next element. So next element is 200, should change the pointer to 200. And in this way, change the pointer to 300, change the pointer to 400, change the pointer to 5, or rather 400 itself will show that the 400th element pointer, next is equal to null. So that's where I said that pointer arrow next is equal to null means you have come out. Then what is inside pointer? Inside pointer I have 400. So pointer is here. This is where pointer is pointing. So let me draw this. So after the loop is run, where is the pointer pointing? The pointer is pointing to, so pointer is no more pointing to the first node because we have taken a loop, looped it through, and we have pointed it to the last element, which is 400. So here is where the pointer is pointing to right now, right? So now the pointer is pointing here, which is okay. What we need to do is we have reached our insertion point. So this step is done, reaching the insertion point. So that is what we have done in step number 4, right? And in this step number, in the earlier head equal to null, what I missed out on saying is this is step number 5 because 4 was not applicable. We were already at that reaching the insertion point. So that's something that I corrected. Now when we have reached the insertion point for the second use case, then what we need to do is the next step is adjust pointers. So what do you want to adjust? You want to insert this particular node you want to insert here. So you have to adjust this pointer, right? So let us take a dotted line and let us say that this pointer needs to be adjusted to what? To 500, right? So we have to change this to 500. And what else do we need to do? So, and by the way, how do we do that? If we have to change this to 500, how do we do that? We already are at pointer. So we can say that pointer arrow next is equal to my whatever is my new node. New node is pointing to 500. So whatever is my new node. So that way, what does this become? This becomes equal to 500. So we are done with one adjustment of the pointer. The next adjustment of the pointer is this particular person, right? And when we are inserting this there, then my new nodes previous should be equal to what? Wherever the pointer is pointing. So if I'm placing this at the end, then shouldn't you think that this should point here from a previous standpoint? So for this node, the previous node is this node. And where is this node? This node is at pointer arrow, or rather directly at pointer. Right? So directly at pointer is what? Directly at pointer is this 400. So the new node is at 400. Right? So what I need to do is I'll need to say that the new node's previous is at 400. So I will say 400 here, and how I will say new node your previous is equal to the pointer, because pointer is pointing to 400, right? And I want the new node to point to 400. So now this is pointing to 400. This is pointing to 400 here, or rather this is pointing to 500, my bad. I wanted to change that. So this is pointing to 500. New node is at 500, but its previous is pointing to 400 because that's the previous. This one is the previous to that new node, right? And the next of the new node is null. These are the only two pointer adjustments that we needed to make. So we had to make this pointer adjustment, right? And be careful when I say pointer adjustments, because there are questions that will come which will ask you how many pointer adjustments are to be done for a particular operation. So you'll have to say how many pointer adjustments. The way I'm drawing, you have to understand how many pointer adjustments you are doing for the new node. Not just for the new node, sometimes you may have to change the head, sometimes you may have to change the in-between links, total number of pointer adjustments, right? So I hope that is understandable. Now let me move on to the so this is where you do the pointer adjustment. So that is your step 5, and I hope that makes it clear, right? So this is what we are talking about when we say insert at end. Complexity, of course, we have to traverse through the elements, and hence the complexity becomes order of n in order to find the exact position of the end. Okay, so let us move on to the next one now, which is insert after a given value. What are we trying to do here? We are trying to insert a particular node after a given value. Now, if the value doesn't exist, then do we need to go through the process of creating the node and accepting the input if the value doesn't exist at all? So let's say I want to insert after 7, right? So I want to insert something here after 7. Then if the value doesn't exist, then I don't need to go through all these steps. Unnecessarily, I don't want to create a node, accept the input. So actually the first step here, if you ask me, should be that accept input for value and check existence. That should be the first step. And if it doesn't exist, for example, here all we are doing is we are checking the input, then we are going through the entire list using a changed variable, which is a pointer variable. We are using head, but we are not using it directly. Remember, any kind of browsing through the linked list, we have discussed it in the last class also, that any kind of browsing, we will take a temporary variable, pointer variable, or whatever you want to call it, but we will not use the head variable. So the pointer will keep on saying that, okay, I'm pointing here. Next it will say I'm pointing here. Next it will say I'm pointing here. Next it will say I'm pointing here. And in this way it will go on and try to find whether in each of these iterations 7 exists or not. And that is what we are doing through this loop. Each of these iterations we are checking whether 7 exists or not. And if we don't find that, then we are saying that we have not found it, so let us return. So this is step number 0 that we have to do for insert after a given value. So we have to first check that given value whether it exists by browsing through the linked list, and then return back if it doesn't exist. If it exists, fair enough, we will start our process. So let us start the process. So what is the process? We know the process. By now we should know the process. Now first things first is we have to create the node. So I'm going to create this node, right? So what do? We do a malloc. So how does the malloc work? It creates a pointer called new node. The pointer points to, let's say, 500, and 500 is actually the area of memory where malloc has created for us. So in this, there are two pointers here, one for previous, one for next. And this new node does not have any data because we have not accepted the input value, right? So we will put the data here. So this is our data section for the new node, but the new node points here. This is our 500. So that is our step 1, create the node. So that is what we have done here. Then what we are doing, we ask for the data. So accept the input. That is what we are doing. Same steps I have kept. So accept the input means these two. So then data goes here. Let us say that again we are trying to put 10 as the data. So 10 as the data will go here through this particular syntax, right? Next we are saying initialize the node. Now initialize the node is what I said. Initialize the node means that if there are any steps that your previous and next pointers will always do, then put that step here. There are no steps here because previous and next depends on where you are inserting it. I don't know that yet, right? I am at least in terms of the steps that I have defined, initialize node therefore does not have anything that needs to be done, right? So I have to reach the insertion point. I have already reached the insertion point because I know that we have already done earlier. So where is our insertion point? Our insertion point, you remember we had pointer and the pointer was moving and it exited. Let's say the pointer exited because it found 207, it exited with 200. So the pointer was pointing here because we want to insert after this node. So this particular loop that we had discussed earlier will make the pointer exit at 200. Right? So when the pointer is not null and the pointer data is not equal to the key, it will go on. But as soon as pointer data becomes equal to the key, it will exit out of this loop. Then pointer is already pointing to 200. Right? So now we know that pointer is pointing to 200 and our new node is like this. So we have actually reached the insertion point through our code at the top. Right? So this is through this we have reached the insertion point. Now that code, therefore this particular line becomes invalid because we have already completed it at the top. Now next is So initialize node, step number 3 is not applicable. Adjustment of the pointers, that's the most important thing that is left. So all of this is my adjustment of the pointers. Let us see what we are doing. This is our step 5, right? So all of this is my step 5. So what do we need to do? Step 1, step by step. All we need to do is, first things, let us see that if we are inserting the node here, then this 300, which is pointing to the next node, should point to 500. So this should be actually 500, right? So this should be 500. That way this starts pointing here. How do we do that? This should be 500, means our pointer arrow next should be equal to our new node. So our pointer arrow next, where is this? This is where it is. Our pointer arrow next should be equal to the new node, right? But we will not do that right now. Why we will not do that right now? Because we lose out on this particular pointer. So if I just omit it for the time being and bring back what it was, this 300 is very, very vital for us, right? Common mistakes that we always do, and which is why I wanted to emphasize on that common mistake, because you go from top to bottom, right? You are seeing a picture at the top and you know that, okay, acha, this has to be changed to here, let us go ahead and change it, because you are seeing left to right, top to bottom. And that is where the problem starts. If when you see left to right, top to bottom, you forget to think logically, and that's where you will change the topmost part, and then you will struggle to actually make sure that this particular gentleman needs to point here. Where will you get this address? If you are omitting 300, you will never get this address. So that is the reason that what we need to do is, we need to get this address first, and once we have adjusted with 300, we can then replace 300. So we will do that, but not at this point in time, right? So let us do this particular adjustment first. So what is this particular adjustment? Let us say our next is actually the pointers next. So our new node next, see, new nodes next is the pointers next, right? So what does that do? That says our new node next is the pointers next. That means the pointer, whatever it was pointing to, that next was pointing to 300, right? 200 was the pointer pointing to, and the next is pointing to 300. So the 300 is something that the new node now needs to point to, right? Because I'm inserting in between, new node is now going to point to the next element, which is 300. So the thing will be looking like this, right? The thing will be looking like this. This will not be there, right? So this 300 here will be pointing, this 300 next should be changed therefore now to the pointer address, which is 500, and we had already changed this to 300 earlier, right? So that therefore now this, if it points to 500, this particular previous should point to 200. So now previous now points here, next points here, right? And then what do we have from the next part of this? The next part of this points to the next node that was there in the hierarchy, right? So with this and of course this 200, this also needs to change. So this 200 will need to now point here, right? So those are the 4 pointers adjustment that you have to do. We have already done one pointer adjustment, which was the 300 part. So we have done this adjustment. Now what do we next need to do? We need to say new node, new node previous. So new nodes previous means what? New nodes previous means this. So we are adjusting this pointer. So new nodes previous, this pointer will now need to be going where? 200 came from where? PTR. So new nodes previous will be equal to PTR. So we are done with this adjustment and this adjustment. We are left over with 2 more adjustments. So now we can actually attack this and this, right? So this 200 now needs to change also. So this 200 will no more be 200. It will therefore now become 500. So this will become 500, and we will therefore have all the node pointers same. Now how do we make these changes? These last 2 changes, we will say that your pointers next, that is this 500, which was not 500, you remember it was 300. We are changing that, right? So we will say that pointers next, which is basically our 300, will now need to change to the new node. So pointers next, the pointers next will now need to change to the new node. This is what we are saying, right? So the pointers next will now need to change to the new node. So that is where we go. Next, so this line is also done. Pointers next is done to the new node. The last step that we have is the pointers next previous. That means, see, you don't have access. Listen very carefully here. This is an important step. You don't have access to this particular pointer. The reason is only you have pointer, right? Pointer points here. How do you know this particular thing, right? You have to change this now to point to the new node, right? So how do we do that? So I will say I know my pointer. So my pointer points here. The pointers next points here. Whose previous is this? So what do I write? I will write pointer arrow next arrow previous. Then only I'll get access to this 500. And this I will say is equal to my new node. That makes this particular connection, right? So that is how we will do an insert after a given value. And that's what I meant by adjustment of pointers. What is the time complexity? Of course, after a given value, the given value is found at the end, then you would have gone through n iterations, and therefore the complexity would be order of n. So that's on the insert. We'll now move into the delete part of it. In the delete part of it, if you see the same example, if I delete from the beginning, then what happens? There are 3 steps only for delete, right? Position the deletion point. The position the deletion point is already done because we are already at the beginning, right? So we know that we have to delete this particular element, right? So this is the element we have to delete. Now, if this is the element we have to delete, what do we need to do? Our head needs to point here, right? So our head needs to point here. That's the first step. How does it point there? Through this. Through this only we will go to the next. So we will say that, again, we will not disturb head. Whenever we are talking about moving around the head, we will never ever move around the head directly, right? So we will take a temporary variable, and in this temporary variable we will put head, which means this temporary variable now has 100, right? And what is the reason for that? I will come to it. Now what we are doing is we have to adjust the head. Yes, that there is no doubt we have to adjust the head. We have to move the head. Why take the temporary variable then? Because anyways we have to move head. So anyways head will change. That is what deletion is all about, right? We will change the head to the actual node, the actual first node after the deletion is done. Now we are not doing that by just changing the head. We are storing head inside temp, and the reason for that I'll come later. Now let us store there. And what we will do is we will say that head is equal to head arrow next. As simple as that. So what will happen? This head will be head arrow next, means this head will become 200 because the next is pointing to 200. So what does that do? That establishes this connection, right? So that's what we will do in head arrow next. And where are we? We are at this step, adjusting the pointers, right? So if this is done, then the next step is what? The next step is the previous of the head, right? So head is right now pointing to 200. So therefore head has a previous, right? Head is pointing to 200, therefore head has a previous. Now do you think that head pointing to 200 justifies this to be 100? Now what is head? Head should be the first element, right? We have deleted the in-between element. Now head is pointing to the second element, but the second element is the first element. So this 100 cannot be 100. The first element cannot have a previous. So the previous has to be made to null. So that is why what we have to do is we have to say that wherever head is right now, it should be pointing to null, right? And that's what we do with this particular line, that the head previous is equal to null. And that's it. That's all we need to do, because what we have done is we have adjusted the pointer. This is one adjustment of pointer that we have done. This is what we are talking about, this adjustment, right? And we have adjusted the pointer of head to point to the second element. That doesn't mean that we are done. That means what we have done is we have cut down this link, but we have to cut down this link also, right? Because now head is the first element. So that's why we will say that we have to cut down this link, means we'll have to make this to null. And at the end, all of that is okay. So this is my second pointer adjustment that we made, but all of that was okay. But what happens to this particular area? This memory, we have cut down the links, but we have not cut down the memory. The memory still is allocated. We have to free this memory. How do we free this memory? We need to know 100. Where was 100? 100 was stored in head. Head is no more there. And that's why storing head was important, and that's what we had done. We had carefully done temp equal to head equal to 100. So now you get it on temp. So free the temp, and that's what will free this permanently. This memory will be available for others to use, and that's how you do delete from beginning. Complexity, we are deleting from the first position itself. Complexity is order of 1. So that's on the delete from beginning. For the delete from end, let me clear up this section so that it becomes neater and clearer for you. Let me bring the template from here. Give me just 10 seconds. Now, if we if we actually talk about this particular section now, which is our delete from end. Now, delete from end, what does it mean? We are talking about delete from end. What does it mean? Delete from end means we have to go to the end and then delete, right? So how do we go to the end? We have to have a traversal routine, right? So there again will be two cases in this particular section where we'll have to talk about traversal, and we have to talk about traversal of a valid list, and we have to also talk about traversal of an empty list. And that is why we will have to do in 2 steps. So we will do the first step first, right? So we will say that the list is not empty. Then if the list is not empty, what do we need to do? We need to traverse to the end, right? How do we traverse to the end? We will take a simple pointer variable, right? So we will take a pointer variable and we will say that pointer variable is equal to head. Remember, I told you that traversal means you have to use head and move it next, and you don't do it with head, you do it with another variable. In this case, we will take a pointer variable. So what are we doing here? We are trying to position the deletion point. So that is the step we are trying to do. So positioning of the deletion point means I have to take a pointer variable, and then pointer variable is equal to 100, right? So our pointer is now pointing to 100. Next, I will make this pointer point to 200. Next, I'll make it point to 300, and next I'll make it point to 400. And when I point to 400, my next is null. So that's why this loop will come out. My next is null. So this will come out. What does the pointer have now? The pointer has 400 now. So the pointer is right now positioned at 400 with that loop. And we know how to do that. So pointer is right now at 400. So pointer is pointing here. This is where it is pointing. So what do we need to do? We will need to delete this node. So I know, okay, this is fine. I can delete this node. I can delete this node by doing a free of this pointer. Perfectly fine. But then there are some adjustments I need to make. What adjustments? This particular person cannot point to 400 because now it will become the last node. If it becomes the last node, I'll have to make this as null. Now, how do I reach this? I am here. My pointer points to 400. I have to go to 300. How do I go there? Because I have to make 300 next is equal to null. Right? How do I do that? So my pointer, which is pointing to the last node, also has a previous. Don't forget that it has a previous. So I will say that pointer, whatever is your previous, that means what is the previous? 300. So whatever is your previous, that is this 300, will have a next. Put it as null. Whatever is your previous will have a next. Put it as null. That is what we do here. And that segregates this link. Now we are ready to free this. Right? So we will say free the pointer. That's all we will do. So this is the way we do it for a particular list which has some amount of element. But there could be situation where the list doesn't have any element at all. In that case, what are we supposed to do? So in that case, if we actually imagine a list which is looking like this, that the list itself says that the head is actually pointing to only one element. So instead of saying empty list is valid for our insertions. The second case was empty list. We inserted one element in an empty list. For deletion, we will say that our special case is when head is pointing to the one and only element, right? So there we will say this is 100, this is 100, and this is null, and this is, let's say, 5, and this is also null, right? So then what will happen? Our pointer, which was equal to our head, will now have pointer arrow next equal to null, right? So which means that it is checking this pointer arrow next is equal to null. So this is only the last element. With this, it understands that this is the one and only element, because head next, or rather pointer next, is null, means that the first element has a next pointer as null, which means the first element is the only element, right? So if that is the case, then all you need to do is, you have understood that this node has to be deleted. There is no existence of this node. So you have to break this chain. How do you break this chain? You have to make this null. So make it null, head equal to null. Then you are free to actually free this pointer. So you have made head equal to null. Because head has now become null, you would have lost this 100 address, because 100 is gone. You are making it null. So that's why you need a pointer to store that 100, so that you can therefore make adjustments to that pointer variable in the future, which is free pointer in our case. So we do a free pointer, and that's all. That will take care of delete from beginning or end. And that's your complexity. If we actually do the complexities, then from the end, when we have to go to the end actually, then the end is an order of n, right? So if we have to traverse till the end, then we'll have to go through all the ends, which means the complexity will be an order of n. So that is all on the delete from beginning or delete from the end. There is also a delete by value, which is typically done in order to check whether a particular value is there and delete that node. Similar to our insertion, remember, we searched for a value and then we positioned our new node after that value. Here we'll search for the value, but we will therefore delete that particular value. In our case, let us assume that we are searching for 7. Now, if we are searching for 7, then the first thing that we have to do is we'll have to get the so I will say that in this case also there is a 0th step, which is typically to do with getting the value to search, right? And also finding the value, getting the value as well as finding the value, right? So we will do that step, which is this particular step, where we do the getting the value and finding the value. It's the same syntax, so I'm not going through it. This. So what you will get is, if you get some value, if you get, let's say I've searched for 7, and then what I will have is, I don't disturb head, right? I have to search. You have to search means I have to traverse this list. If I traverse this list, what I have to do, I've already told you, get it inside another pointer variable and move the pointer variable to check whether 7 is there. Suppose you found the pointer variable with 7 there. So pointer now points to 200. So pointer is pointing here. You have to delete this node. What adjustments do you need to do? Right? So let us take 3 cases here. Case 1, if it is the first node. In fact, because we said we are searching for 7 and 7 is the middle node, I will take case 3 first, which is this particular portion. Okay? And we'll come back to case 1 and case 2. Now case 3 is when it is a middle node. So we have found this in the middle. Now if we have found this in the middle, what adjustments do we need to do? Simple. What we will do is, this particular node has no existence going forward. That means this particular link will have to be established. The next will have to point here, and this previous will have to point here. Then only I can say that my links are properly established. So what do? We will say pointer. So how do we change this? We are at pointer, right? Pointer is 200. So we will say pointer, you have a previous. So this is your previous. Pointer, your previous is this. Where is it pointing? 100. So go there. So pointer previous next is what we want to change. Pointer previous next, we will change this to what? Pointer next. So pointer previous next will be changed to pointer next. Right? So pointer is this. Let me draw this again. Let me use a different color. Yeah. So pointer, this is pointer previous. Pointer previous is this. Pointer previous is this. So previous is pointing here. Whose next is this? Right? So whose next is this? And what do we put there? We put pointer arrow next. What was pointer arrow next? Pointer previous next is pointer arrow next. Pointer arrow next is 300 because pointer is pointing here. So pointer is 300. So that's why pointer previous next is pointer arrow next. And we also have to set this. And this is just the reverse, which is pointer next. Pointer is pointing here. Next is here. So pointers next. Right? So pointers next, whatever is the previous of that. So pointer next, whatever is your previous value, you will need to go to pointer previous. Pointer previous is 100. So you will have to go here. So pointer next previous is equal to pointer previous. So that is all that you need to do. It's very easy for you to understand as long as you can figure out this arrow, what it tries to tell you, because you only have access to PTR, which is 200. From 200, you will have to adjust, go here, adjust it. You have to use this, you have to use this, and you have to use this. How do you get to these four is what you need to understand. One will be pointer next, one will be pointer previous, one will be pointer previous next, and one will be pointer next previous. Where you use that, I hope you can probably understand and use it to your judgment. Let us talk about case 1, which is when we are trying to delete the first node. Right? So if we are trying to delete the first node, again, what will happen? The thing that will happen is my pointer will be equal to head, and it is the first node, which means that we have searched for it and we have not found it, or rather we have found it. Where have we found it? Okay, let's say that we are searching for 5. So our search element is 5. So if our search element is 5, our pointer will be found at 100. Through what? Through this particular loop. Right? So our pointer will be found at 100. Right? So pointer will come out saying that 5 exists at 100. Come out. Now, pointer is 100. Head is also 100. Then what does it mean? It means that we have found it at the first node. Right? So that's what we will check here. If pointer and head are the same, which means the found element is equal to the head. Hence, there is only one element. And then what do we need to do? All we need to do is we need to put head as head arrow next, because this has to cease to exist, which means this link has to be removed. That means this has to point here. Right? So this has to point here. Let me just see if I can delete the previous drawings to whatever extent I can. Yeah. I think this is enough. Okay. So my pointer, as I said, I'll not repeat it. My pointer is right now at 100 because it got 100 as the node which had we were searching for 5. It had 100 as the node which was being searched for 5. Right? So pointer is now pointing to 100. So pointer is not pointing here. Pointer is pointing here. Now, because pointer and head are the same, we can now take the liberty to say that this particular element is the first element. If it is the first element, where should our head go? Our head should actually go to the next element. So our head should point here. Right? So what is that? That is pointer next. So our head should be equal to pointer next. That's all. So if our head is pointer next, then this link gets broken, which is so good. We wanted that, but this link still stays. This link still stays, right? So what do we have to adjust? We will have to adjust the head previous. right? So where is head right now? Head is right now pointing to 200. So head has become 200. Why? Because we said head equal to pointer, next pointer was pointing to 100, next was 200, so head becomes 200. Now I also have to break this link, right? So this link shouldn't be there. This link should be that this should be null, because this is now the first node, so it should be null. But how do I get here? It's very simple, because we have this as head. The head arrow previous. Where is our head? Head is 200, right? So we have to adjust 200's previous. But 200 is represented where? Inside head. That means it is head previous, and that will be equal to null. That's all. And at the end, we will anyway free pointer. For all the cases, we will anyway free pointer. So no, don't worry on that. That free is common to all the three cases. So that's your case number 2, or rather case number 1. Let us see case number 2, where the deletion happens from the end, right? In our case, let us say that the value that we are searching is, let's say, 5. In fact, this is also 5, that is also 5. Let us say this is, for our sake, this is 15. The value we are searching is 15, right? So then we are searching for the last node. Now when we are searching for the last node, then through this particular section, where will we go? We will go to the last node, right? And our pointer will point to where? 400, right? So our pointer now points where? Not here, pointer points here. Now when the pointer points here, then what do we need to do? We need to delete this node. So in order to delete this node, what are we trying to do? So we are trying to position our deletion point. That step is done. We are trying to adjust the pointers. Adjust the pointers means what? Adjust the pointers means we have to break this link. That's all we have to do. So if we have to break this link, all we need to do is, we are at 400. We have to go to this previous node. How do we go from the pointer to the previous node? From the current node to the previous node. We will say current node's previous next. That's what we'll say. Now in our case, current node is pointer. So we will say pointer, your previous is this, that next is what I want to adjust to null. That's all we will say. And that's what we have done. Pointer previous next is equal to null. And that's your adjustment of pointers. As I said, at the end, we will do all the frees. We are doing all the frees at the end. So this is your delete by value. Complexity, the worst case complexity will be when it is at the last node, and hence the complexity will be order of n. So that's on delete by value. Then we have some chota mota things in terms of traversal as well as in terms of search, which we have already covered. So I'll not be going details on this. You have how do you traverse? We know that we have to take a temporary variable like a pointer, which we will have to assign to head. Then we will have to say a loop where the pointer is not equal to null, right? We will have to go on. So we will have to take a star pointer here, star pointer, which is 100. And then we will have to say that this pointer is pointing here. We will keep on changing. We will print the data. We will print the data. And then we will move it to this next. The pointer will now change to, this pointer will now become, taking the cues from this 200, this will now become 200, right? If it becomes 200, then initially it was pointing here. Now it will point here, check print 7, then it will point here, print 3, then it will point here, print 5. So that's all it will do, right? So that's what is happening here. Right, so it is printing and then it is doing pointer. And next, I hope you can understand, because this particular portion we have covered almost in every other code in the previous few minutes. Right now, if the most important point of a double linked list is that you can traverse backward also. Like a single linked list, you traverse forward. By the way, the single linked list code for traverse forward will be the same as what you see here in terms of the double linked list. But only thing that you have to remember that the advantage of using this double linked list is that you can traverse now backwards also. So to traverse backwards, first you have to reach to the last node. So we will use the same pointer concept. So we will say the same pointer with a star, and then we will say that you are at 100, and then we will say that please move from here to here to here to here till you get a null, till you get a null, till you get a null. And then what will happen? The pointer will therefore come out at a value which is equal to 400. So now my pointer is here. Now, can I move in this direction? Of course I can. Why? Because I have previous. With this previous, I will go to the previous row. Just like with the next, you go to the next row. With the previous, I'll go to the previous row. So what I'll check? I'll check this null. Till the previous is null. Right? So my pointer will be actually pointing to a particular node, and then that node should not be null. When it becomes null, I will stop my loop. Till that time, what I will do, I will say my pointer, which is 400, that data is what I will print. And then I will say pointer equal to pointer previous. So pointer then comes here. Again, the data is printed. Pointer previous, pointer comes here. Data is printed. Pointer previous, pointer comes here. Data is previous. Pointer previous is null. So pointer becomes null, comes out of the loop. Complexity, order of n, because we have to traverse the entire list. So that was your traversal for the pointers. Next, we will actually do the last portion of this double linked list, which is the search operation. Again, very simple. Again, we have to take a pointer. Anything traversal, we have to take a pointer, which is pointing to the head, right? And all we need to do is that we will have to say that check whether the pointer becomes null. So this means that all we are saying is pointer, you are at 100. Please check the value at this 100. So the value at this 100 should be equal to the key. If it is, come out. At the position. So we have taken another position 1, right? Just to make sure that we explain to the user at what position it is found. So position is 1, then position becomes 2. So when you come out, you print where you have found it, and then you come out, right? So if we are searching for any kind of element, then the pointer's data will be checked. If it is not found, this pointer will change to 200. If it is not found, this pointer will change to 300. If it is not found, to 400. And if it is not found, 400 will become null. And when it becomes null, the pointer will exit, right? And when the pointer exits, and how are we moving the pointer? By the pointer arrow next. And when the pointer exits without any finding any position, we will print not found. So that is how we will move. So if our pointer has become null, that means the element was not found. So we will print not found. Right? Because if it is found, we will never reach this line. Why? Because we have used a return. So if it is found, we will print the position and we will return out. So let's now see the circular part of the linked list, which is the second topic of our discussion. And we have completed double linked list. We have checked all the operations in details. Circular linked list, most of the operations are similar to double linked list. So while I have given the algorithms for all of them here, I'll not go to that level of depth as we did in the double linked list. Of course, you can rewind and watch the algorithms for a better clarity in case you don't understand what we are discussing on the circular linked list. Everything that is similar, I will go a bit faster. Everything that is dissimilar, I will of course spend ample amount of time in order to explain you to the nitty-gritty. Now, what is a circular linked list? A circular linked list is a linked list where the end points to the head. That's all. Where this end, which was null, now points to the head. So basically you have taken the end and put it at the back. Put it at the front of it, not the back, sorry. You have put it at the front of it. That's all you have done. And it's minded, it's not a double linked list. You can of course do a double linked list, but it's not a double linked list. It's a single linked list whose last node, which was null, is now pointing to the first node, which is the head. That's all. So what do we have? We have the structure the same as a linked list. There is no change, right? Same as a single linked list. There is no change. And instead of head, we are storing last. What is the reason of storing last? Why not head? Because if I store last, then if I store last, where is last pointing? Let us say last is pointing to some address. Let's say this is 4000. So this is 4000. So last is pointing here, right? So if last is pointing here, using last or at last, I can do a lot of operations which saves an order of n. What operations? Insert at end. Can I do this without taking head and traversing like this and going to the end, going to an order of n and then doing the insert? I avoid that because I have the last. So I know insert at end I can do with an order of 1. That is the reason why typically we will have the last here. What about beginning? You have taken this at the last. Now how will we do at the beginning? Insert at beginning. Very simple. Insert at beginning would mean last arrow next. Last arrow next will point you to the head, and the head is the beginning. So do that there. So that is also available for you. Only thing that is challenging is in between, but it has taken care of the traversal that was needed to go to the end by the circular linked list. Operations are similar. These are the three operations, same as that of the double linked list. These are the three operations, same as that of the double linked list. And again the traversal and search. So remember that instead of head, we use the last. Some short question can come. Where do you use last? Which linked list do you use last? You have to mention circular linked list. So the next that we go to is the insert at beginning, which is the first operation, in fact. So let me take a standard one or single linked list, which is looking like this. I will not worry about the addresses that we are storing. Let's assume that standard addresses are getting stored. Only difference that we'll have to establish here is that there is a tail, or let's not call it tail, let's call it last, right, which is pointing to the last element. That's the way we have defined a circular linked list, if you remember, right? So if this is at, let's say 300, this is at 200, and this is at 100, then what we are saying is this last actually contains 300. Therefore last is pointing here, right? So last is pointing here, and we also have this last being taken back to here. So last is pointing to 300, and 300's next is pointing to the first, which is 100. So that is the scenario that we have to start with, right? Again, here there will be two cases where there is no elements in the list, and when there is elements in the list, right? So let us take the first case as elements in the list. So this is the case that we are talking about. There are elements in this list, and we will have to insert at the beginning. Beginning means what? Beginning means here. So we'll have to insert at the beginning. So what we need to do is we need to create a node. So we will have to create a new node. I'll not go to that syntax part of it. So we are talking about creation of node. We are doing that here, right? So that is the first step that we are doing. So the new node that is being done will have some data. Now the new node is, let's say, created at a 500 address, and that at that 500 address, what do we have? We have, by the way, I hope you understand this has an address component to it, which I have drawn through this vertical lines, and the new node also has an address component to it because the structure is the same for both. And therefore now the next step is for us to accept the inputs. So accepting the inputs will be through this particular line. This step is done. So we have accepted, let's say, an input of 7. We want to insert 7, right? So we have accepted an input of 7, and that new node, which is pointing to this 500 address, is now having the data as 7 through this step, which is our accept input step. Now we have to initialize the node and make it to something that will always be valid. Now, when we actually talk about the new node, which has to be inserted at the beginning, then there is nothing that is always valid, because the new node's next address has to be the address of this 100, right? So we are inserting at the beginning. That means the new node is coming here. So that is where the new node is pointing to 100. So the next address has to be 100. Now this will not be something that I can directly write, because I'll have to understand it from variables. I cannot directly write nulls. So when I say initialize the node, it means that can you do it a null directly, like at the end of the linked list, the last element inserted is always null, right? At the beginning of a linked list, for a double linked list, the first element inserted, previous will always be null. We are talking about that. So this initialize node is not applicable in our case, right? Particularly this particular use case. So what do? We will need to now therefore say that my new node, whatever that new node's next is, now where will it point? It needs to point to 100. I know it has to point to 100, right? So it has to point here. How? I don't know 100, but I know last has 300, and last's next is actually 100, right? So last's next is 100. So can I say my new node next will be equal to last next. My new node next is here, is equal to last next. That means I am establishing this chain. New nodes next is equal to last next. That's all that we did. Now, then my last element, this 100, is becoming invalid because the new person has come here. There is a new person who is this. So this is my first node now. This is my second node. This is my third node. This is my fourth node. Now the fourth node has to go back to the first node, right? If you remember, so we have to break this link. So the fourth node has to point here. So the fourth node is last, right? So the last arrow next is this. Should be going where? To the new node, which is at 500. So we will change this to now 500. That's it. That's all we will do. So that's all we will do, and that's all that will be there for insert at beginning. So what did we do? We have done the pointer at the initialized nodes were not there. We were inserting at the beginning, so we had reached the insertion point. We therefore adjusted the pointers. So we adjusted 2 pointers, 1 pointer here, 1 pointer here. So that's all that we did. So that is this particular example. Now, if we take the other use case where we are talking about, by the way, the earlier example had this as 5 because 3 and 4 was not applicable. Now, if we take a use case where we have let's say a null. In fact, we don't have anything, so we have null. So our last is actually equal to null. So our star last, which was a pointer, is pointing to null. This is a blank list. So if it is a blank list, then this particular line takes over. The first 2 sentences or first 2 steps were the same. Only thing that we are now doing is we are now, and initialized node is also not applicable. So first 2-3 steps were the same as that of insert at beginning. All we are doing now is reaching the insertion point, which we have reached, right? We have already reached it because last node is null. We know that this is the last node. This is an empty list. We have to insert here. So what do? We had created a new node, remember, through the first step. So that new node was having a pointer, which is, let's say, 500, and that 500 was looking like this, right, with 7 inserted here, and this was null or junk, right? So all we need to do is, this is 500. So all we need to do is we will have to have last node point here, because this is the first node. Last node points to the first node, right? So the last, and this is also the last node, right? So the last node will point here as well as it will be the first node. So the new nodes next, what will it be? So the new nodes next, this next, because this is the last node. Now this is the only node. So it's next, it's the first node as well as the last node. Now, if it is also the last node, then this last pointer or the next pointer should point to itself. So this is 500. So we should say that our last node, or rather we should say first that the new node, your next, is equal to yourself, because you're the only node, and next is supposed to point to the first node. So if new node is here, new node is also the first node in this side and also the last node in this side. So we know last node has to point to the first node. So that's why new node next is equal to the new node as the address of that. So we now have that, and because we have changed that, our last now cannot be null, right? So our last now has to point to new node. So we will say last is equal to new node. So last will become 500. So last is equal to new node. That's your use case 1, where the list was empty. And of course, for the beginning, the order of adjustment or the order of complexity will be 1. Next, we are talking about insert at end. Insert at end is again pretty simple enough. It has again 2 cases. If we are talking about this particular list, then in this list, this is the end, let's say, and we are having a last pointer, and that last pointer, let's say these addresses are 100, 200 and 300. and the last pointer is pointing to 300. And of course we are talking circular linked list, my bad, this should not be X, this should be pointing to here, right? So that's what we are right now having as the starting point of this particular example. We are trying to insert at the end, so we will have to create a node. So the node is called new node as a pointer, and that new node pointer has, let's say, 400 as the address, and in this 400 address we have the node which is having this data. So that first step is done. Second step, accept the input. So we will accept the input at, let's say, 7 is supposed to be inserted, right? We are trying to insert 7, accepting the input. Initialization of the node, nothing much to initialize here. We will not be initializing this node. We cannot initialize this node to anything that is default. Default is null. Can we initialize this new nodes next to null? We cannot, right? So we will have to therefore rely on the business logic that is there for this particular example. So what is our new nodes next? Our new node next, do you think our new node, when the new node comes at the end, then what should happen? First things that will happen is this pointer will cease to exist because this now becomes the last node. So our last node should actually point to this node because this is our last node, right? And this last needs to change. Therefore, this last also needs to change. The last is pointing here. The last should start pointing here because that is our new last node. So how do we get this particular address? I have to change this address, right? So I have to remove this address. I have to make this address point to this address, right? So I have to make this address point to this address. And I have to also make the new node point to the first address. So how do we do all of this? There are 3 things that we will have to do. So these 3 things, let's take it one by one. So let's talk about new node next, this particular element. New node next, where does it go? Our new node next should go to our last next, right? So why is it so? So see, if I say 300 here, new node next is equal to 300. So my last, rather not 300, my bad, last is 300. So last next is pointing to the first. So that's what we wanted. So we want this to be equal to 100. So our new node next should be equal to last next because last is at 300. 300's next or last's next is already pointing to 100. So we are saying we will take that 100 from you. So now we start pointing there. So this new node is pointing there, but we have not removed this link. This link is still not removed because last is still pointing. Last next is still having 100. That last next has to change. That last next now has to go to new node, this one. That last next has to go to new node. So the last next will go to new node here. And now this becomes your new node. So this is what we are establishing now. This becomes your new node. So last will now become 400. So that is what we did here. And that's all that we need to do, right? So that's how you do the insert at end. Now for the insert at insert at end with the caveats that we talked about. 1 minute, let me clear this up for you. Yeah. So for this particular insert, this particular use case where we are talking about that we are inserting where last is equal to null. So our last pointer is pointing to null. That means there is no last node. That means there is no first node also. If there was a last node would have pointed to first. So there is no last node first node. That means this is an empty list and I'm trying to insert at the end. So all we need is new node. And that new node, which was, let's say, pointing to 500, had 500 here, and we had a next, and we inserted 7. So all we need to do is we have to say your next is yourself. Your next is yourself. So your next is yourself. That's what we said, right? And last, which was null, will now point here. Last, which was null, will now point here, and that's all. That's all that is there in the first case, where we are actually talking about a empty list where we are inserting at the end. So, and how about the complexities? Of course, it will be 1 because we are not running any loops. Insert after a given value, right? So this is we have completed insert at the end, insert at the beginning. Now that, of course, the third operation is insert after a given value. Now what do we do there? Again, we do the same thing. Insert after given value. Three cases should be there. Actually, from a deletion standpoint, there will be 3 cases. From an insertion standpoint, we'll have to go to the actual position and we will have to insert it just like we did it in a double linked list, right? So let's assume that we are having a list like this, right? So let us assume like this. So this is the list, and we have these as the addresses, and we have a last which is pointing to, let's say this is 400, so the last is 400 and it is pointing here. That is what it is doing. So we have 100 here, we have 200 here, we have 300 here. Now what we are trying to do is, suppose we are trying to find this particular position, insert after a given value. Suppose the value here is 5. We are trying to find out the value 5. So what we will do, first things that we have to do is, again, we will not create the node first, just like we did not for the other cases in the double linked list. So we'll create a step which is basically searching for or getting the element from the user, getting the element and searching for it on the list, searching in the list. That is first step that we will do. So we will take the element from the user. See, we have taken the element from the user, and then what we will do is we will search that element in the list to get to our first value. Now what we are doing is, in order to do that, right, so we will have to first take a while loop or a do while loop. In this case we are taking a do while loop. What we are trying to do is, we are saying that we will take, as you know that if we have to browse, right, we have to browse means this particular searching the list, this particular point is what we are talking about. So we'll take a pointer which is actually equal to last arrow next. What is last arrow next? Our head, right? So as simple as that. So this becomes our head. So starting head, we can therefore start browsing. So we have taken pointer equal to last arrow next, because browsing needs to start from head. Head is where? Last arrow next. This is our head, right? This is our head, and which is what? Last arrow next. This is our next. So last arrow next. So this is our last, which is pointing here. So last arrow next is this. This is pointing to the head. So last arrow next is what? The head, right? So that's what we have established. Now if we run a loop to check whether the pointer data is equal to the key, right? If the pointer data is equal to the key, now we have done this code a bit differently. I wanted to show you a way by which we can do everything inside the search loop, the transaction loop of the searching of that item. Instead of searching that item, putting it in a pointer and coming out, and then utilizing the pointer to insert, I'm saying that inside the loop itself, I'll do the insert and then come out. So that variation is what I wanted to show you, and which is what you see here. I've done a do loop, and in that do loop, what I'm doing is I have found the element. So the pointer was here, pointer was last arrow next, and then the pointer was, therefore let's create a pointer, and this pointer was at last arrow next, means pointer was at 100, right? So now the pointer started changing. Pointer became 200. Pointer became because how does the pointer change? Pointer last arrow next. So the pointer becomes, every time the last element, that next is what we are actually doing till the pointer is not equal to last arrow next. The loop is getting executed through this line, which is pointer equal to pointer arrow next. Of course, the pointer will be always going to the next. We are at the head, we are doing next in order to move down the chain till what? Pointer is not equal to last arrow next. Right? So pointer is not equal to last arrow next means that the pointer is at head and your last arrow next is also pointing to head. That means you have moved forward and you have reached a point where you are at last, whose next is pointing to yourself, right? So which means that you have covered the entire chain. So that's what this line actually means, right? So now if you understand that part, the while pointer last not equal to last arrow next is actually holding you from creating a scenario where, because you are moving forward, you have reached a point. Let's say I have reached 400. I have not found the element. I have reached 400. Then my pointer is at 400 and the 400 is not equal to the last arrow next. What is last arrow next? Last is 400. What is next? Next is 100. Right? So pointer is not equal to last arrow next. So I will go one more time. Right? So I will go one more time. So then what does pointer become? Pointer becomes null. What is last arrow next? Last arrow next is also null, right? So because the last arrow next, whenever that last arrow next is coming, that last arrow next will be coming to you, because it is at the end, it will always be null at that point in time, right? So we are trying to see that if we are moving forward, then at some point we will come to a situation where our pointer has moved to such an area where it is equal to last arrow next. Right, so this is last, and I'm trying to redo the explanation again just to make sure that you understand it. This is last, so the last arrow next is my head. Don't forget that my last arrow next is my head. So if I start from this pointer, which is my head, and come back to head, then I've covered the entire list. So that is what I'm trying to say here. My pointer is equal to last arrow next means the pointer is which started with last arrow next has come back to last arrow next. Pointer started with last arrow next here, has come back to last arrow next. That means it has come back to head. Head has become head again. Head was moving, right? Pointer was moving means from head it was moving. Then it went into a circle because it is a circular linked list and came back to head. So we get out of it. So I spent some time here just to make sure you understand this loop. Now, once we have done this, then we are going to accept the node. We are going to accept the input, create the node and accept the input. So we have done this. Creation of the node is through this line, which is our point 1. Then we are accepting the input, which is here. Then we are saying that the adjustments, right? So what we are going to do is, we have already reached the insertion point. So this step will come at the beginning because we are doing a do loop now. So this step comes at the beginning where we are reaching at the insertion point. So once we have reached this insertion point, we are doing the rest of the steps. We are creating the node, we are accepting the input, because there is no point creating the node without reaching that point. So just like the other example, we are doing the reach the insertion point ahead of actually accepting the input. Now once we are done with this, we have the new node arrow next is equal to pointer arrow next, which is the pointer adjustments that we will do. Let us see how it happens. So for us, our pointer now points to 300 because we were searching for 5. So if this was 5, it will come inside this if. So when it is 5, when the pointer is actually at 300, so the value of this pointer is right now at 300. Now what we are saying is, we had created a new node. We had specifically created a new node. That new node was having a data of, let's say, we wanted to insert 7 and it was at 500, and this new node was pointing to this 500, and that is what it was. So what we are saying is that we now need to adjust this pointer, right? So we have to just, I'll clean off this so that I can explain to you a bit better, get some more real estate. Yeah, done. Now we have created this new node, and now what we are trying to do is, we are trying to adjust the pointers. What are the adjustments that we have to do? Now we have, where is our pointer? By the way, don't forget our pointer. Our pointer is right now pointing to 300. So the new node's next should be where? Now this is where I want my new node. So my new node next should be this. But where is that? Our pointer next is pointing here. So this arrow should be replaced, right? So this arrow will cease to exist and this arrow should replace. So let us create this arrow first. This arrow means new node next is equal to pointer next. That's what we have written. New node next is equal to pointer next, right? And then the pointer next, this line we have to remove, right? So we have created this pointer, this adjustment, but we have to also remove this line. So if we have to remove this line, where does this particular line need to go? It needs to go here, right? So then from here it will come here, then from here it will go up, which we have not done. But then we have removed this line to ensure that our pointer next is equal to new node. So pointer next is equal to new node, right? And that's all that we are doing. So then what we need to do is, if pointer equal to last, which means that we have reached the last node is the area where we are inserting, right? So that is what we are trying to probably adjust. By the way, if the pointer is not equal to last, then this is all that you need to do. Why? Because all you have done is you have moved this pointer here. You have moved this pointer here, and you have adjusted the pointers next to the new node, which is what you wanted. That means all you are doing is instead of here, I can say that I will draw it here, right? So you have adjusted the pointers next to the new node and the new node next to the pointer next. So that's all that you have to do. Now when you have done this, this is perfectly fine. This has no changes to last. But remember that if this was the last element where you were inserting, and we will take that example now, if this was the last element, so I hope you understand here there are only two pointer adjustments. If it is an intermediate element, there are only two pointer adjustments that we have to do. But if there are an equivalent number of elements which we have to traverse as equal to the number of elements, which means that my element is at the last element. So this is how it looked. This is 100, 200, 300. My last was here, and the last was pointing to 300, right? If this is the case and my element being searched is 7, right? So we have 5, 3, 7. Now if this is the case, then what do we see? What should we do? We see that I'm searching for 7 means I will reach last. Who will reach last? Pointer will reach last, because through pointer only we are traversing. So pointer will become, first it will become 100, then it will become 200, then it will become 300. Right? So pointer, remember we had said pointer equal to last arrow next. With that we started. So pointer was pointing to the head, right? We said last arrow next is head. So pointer last arrow next means pointer is pointing to head. That is 100. 100 changes to 200, 300 through this particular line. And we have also explained this particular while loop, right? So this is something that we have already done. Now this 300, which is the pointer, this pointer is also the last, because pointer is 300, last is also 300. So pointer is equal to last. That means my insertion is happening after the last element. That means my last element should change. So that's all you need to do. You just need to change the last element to the new node. So this last element cannot be 300. This last element has to be, so we have to break this link. We have to break this link and make this link go here. That's all we need to do. So my last element equal to the new node, right? The rest of the stuff we would have already done. These two adjustments we have already done, which is to say that this 7th record, or the record that was last, will no more have this particular linkage. So the linkage that we'll have is the last element who's next, or the new node which is the last element, whose next will actually go to pointer arrow next. So pointer is 300, the next is actually the head, so this next will go here. So that way we have created this link, right? So last is pointing to the last, new node is pointing to the front. All we need to do is create this link, right? So that we create the insertion at end complete, which is what to say, pointer arrow next is equal to new node. So that is also something we have done. So these two steps anyway happen. Only thing is the insertion at last is what we are trying to do, that if it is inserted at last, what all changes we have to do. Complexity, because we are inserting after a given value, it will be an order of n. So from a deletion standpoint, it's going to be the same as almost the same, rather I would say, as the double linked list. So we have this as, let's say, our list, and we have this as the circular part of it. Now all we are saying is that there are these, this is the checklist basically. So, and what we have to do is, first we'll have to check the list is empty, then we'll have to position the deletion point and all of that. So let's go through that. First, check the list is empty, because you're deleting it. Of course, you have to check whether the list is empty. So that is your first point, right? Now what you are doing is, you are trying to store this particular first element inside a variable called temp. Why? Remember that we have to delete this element. So we need a reference to this element stored somewhere as last arrow next. So our last arrow next is the first element, which is the head. So start temp in turn becomes head. So we have stored head, but we have stored it in a different way, so that we can later delete this head by calling what? Free temp. This is why we are storing it as temp equal to last next. That's the only utility. Now all we need to do is, this link needs to come here, right? And this link needs to go away, right? So these are the two things that needs to happen. So my this last element's next is what we need to adjust. Why? Because what is my last element? I did not point the last element. So let us say my last is here. Let us say this was 100, this was 200, this was 300. So this 300 is pointing here. So that was my last element, right? So what we are saying now, that if my last element's next, so my last element's next is this, where is it pointing? It is pointing to the element we are trying to delete. Where should it point? It should point to the element which is temp arrow next or the head arrow next. So this is the line we are trying to build. So last next is this, right? Last next, that is here. Last next is this. Where should it go? It should go to the second element. How do we go to the second element? Temp arrow next. Temp is the first element, arrow next is the second element. So that is what we do here, right? But if we have only one node, that is, we are trying to delete from beginning and there is only one node. So the situation is like this. This is what we are trying to delete. That's all, right? So then where will the last next go? There has to be some area where the last next will go. So the last next will become last. Last next is equal to last. What is last? Last is 300. So in our case, when there is only one element, then last will be 100. There is only one element, right? So last will be 100, right? So if the last next, what will be the last next? This is my last element. This is my last element. Suppose it has 5. Its next is there. What is the next? If this is the only element, don't you think the next will be here only? We have done that earlier. So my last is pointing here, which is fine. Last is pointing here. Last is pointing here, which is fine. So last is pointing to the last element, which is the only element. So if that is the case, then what do? We will say that the last arrow next means what? The last element is this, arrow next is this. What is the address here? 100, because that is the last element. So it should go back to itself. So it's equal to last. Then it is the only element, and we are trying to delete it. Then what will we say? This last has no significance. This last cannot point to something which we have deleted. So this last has to become null. So that is what we have done here. Last will become null. Right? So that's how we will adjust our delete from beginning. Now let's go to the next, and of course complexity, because we are deleting from the beginning, complexity will be order of 1. Next, go to the delete from the end. We'll check the list empty. Then if it is only one node, then what will we do? Delete from the end. Only one node is there. Now if there is one node, again the same thing will happen. Suppose this is at 100. My last is pointing to 100 and my last next is pointing here. I want to delete this. All I need to do is make this null. And before making it null, I want to store this somewhere. Right? And how do I understand this is the only element? We will check last, your next, is it equal to yourself? Last, your next, is it equal to yourself? Then you are the only node. Then I'll free you. I will free you first and then I'll make last equal to null. I'll free you first and then I'll make last equal to null. That's all we'll do. So this is for the single element. If there are multiple elements, then we'll have to run a loop to go to the end so that we can delete from the end. So this is my end. Right? So if we are here, then all we need to do is take a PTR and PTR will be last arrow next, because I said we will start from the head. Last arrow next is always the head. We know that by now. Last next is the head. So PTR is here. And this is 100, this is 200, this is 300. We are supposed to delete this. Right? So what PTR will do? PTR will traverse to the end. How will PTR know that it has reached the end? Again the same thing. PTR next will not be equal to the head. So by moving forward, at some point it will come back to the, at some point it will come back here. So it will go here, then it will go here, then it will come back here. At that point what happens? At that point PTR whose next becomes equal to my last. Right? So PTR's next equal to my last. Right? So if that is the case, PTR's next has become equal to the last. What is PTR next, by the way? PTR next is the last is supposed to be what? The last element. So now what is PTR next? PTR next has reached the last. So I am increasing the last, increasing the PTR next, and finally I reach a stage where it becomes equal to the last. Then it is actually reached the end point of this particular loop. Right? So it has started from 100, 200, 300. PTR next is actually 300. Last is also 300. So I have reached the end. I'm stopping there. So what will happen is my PTR will contain 300 at this point in time. So all we need to do now, what we are doing, remember we are trying to delete 300. So all we need to do now is that the PTR's next will be equal to the last next, which means what is last next? Last we did not store. Again we will store last. Last has 300. Right? So the last next is the head. Right? So the last next is the head, and PTR's next is equal to last next. Means, where is my PTR? My PTR is supposed to be, let us see the loop again. While PTR arrow next not equal to last, PTR equal to PTR arrow next. So PTR arrow next is not equal to last. So that is where it stops. So we had wrongly assumed that PTR goes to the last, but PTR doesn't go to the last, because what I missed was that PTR arrow next is not equal to last. So if you understand it, let's go back, let's step back. Don't worry, we will step back. So what was PTR? PTR was last arrow next. That means PTR was head. Let us make PTR as head. So let us make this as 100. What is it doing? It is saying PTR arrow next. Go on doing PTR arrow next. So 100 will become 200. Now at 200, check whether PTR next is equal to last or not. PTR is 200. PTR next is this. What is that? 300. But 300 matches with last. So PTR next is 300 for 200. Right? So it is equal to here. So it comes out. So what is PTR? PTR is 200. So we are right now at 200 and we have reached that node which should be the new last node. Right? So my PTR next, which is this, should be equal to last next. What is last next? The last is right now at 300. So last next, PTR next should be 100. Last is 300. 300 next is 100. So I am trying to remove this link and I am trying to make my PTR next. PTR is at 200. So this is what I am trying to establish here. PTR next is equal to last next. So last next was this link. Right, so that same link I'm copying here and saying that PTR next, your next is which is your link is actually established like this, and I don't need last anymore, so I can remove last by free. So that's all we will actually do for the end, and the complexity of this again going to be because we are traversing, it has to be an order of n. So that's on the end part of it. Delete by value again has 3 cases, and this is a question that has come I think 2 times, so be careful about this. So first things first, we will check if the list is empty. If the list is empty, then we do nothing. Then we will take what element we want to delete, because this is not delete from beginning or delete from end, this is delete by value. So we take that element from the user. So we will take that element. Let me draw this. So this is a 4 node linked list, and this points here. We want to delete, suppose, an element which has 5, and this is how it looks like. And our last is here, which is having 400. This is 100, 200, 300, and 400. And this 400 is therefore pointing to this particular node. This is the current situation. What are we trying to do? We are trying to find this element and delete it. So what all we need to do? There will be various cases. We are talking about case 3 now, where it is in the last or the middle node, just like the same circular list example. So what we will do? We will say that, where are we stopping? First of all, let us see where we are stopping. So first things first, we'll have to traverse a loop, and in that traversal of the loop, we will have to check whether the data is actually equal to the key. So we have taken traversal of a loop means you have to take a pointer. Pointer will be equal to what? The head. Head is what? Last arrow next. Right? So that is how you will have to think. So till my last arrow next does not become the same way. We have done the while loop here with a pointer equal to pointer arrow next. A do while loop, same way. Right? So we have done again a do while loop with pointer equal to pointer arrow next, and we are moving that pointer till pointer becomes equal to last arrow next, which means pointer has come back to the head. Right? So in that case, what will happen is my third case, which was here, our pointer is right now at, let's say if we take the pointer, then the pointer was originally 100. Last arrow next is 100. So pointer was originally 100. It became 200. It became 300. And thereby it entered the if, because data was equal to key. It entered the if. It entered into this particular case. Right? What is this case? It says previous arrow next is equal to pointer arrow next. Now what are we trying to do? We are trying to remove this link. Right? So if we are trying to remove this link, we are also storing something as previous. So we need to take that variable also. Previous is also a pointer. And as it goes forward, right, and that's the intelligence of code, as it goes forward, because you have exited here, your pointer is 300, you are here. How do you know your previous node? You are not in a double linked list. So store a previous value, and keep on incrementing it as you move forward, right? So that it always points to the previous element. So that I hope you can do, which is if last arrow next is the current element, then last is your previous element, right? So that is what it is. Pointer is my starting point, my previous therefore was last, right? And in this way, as we move the pointer, we will also move the previous. The previous will become equal to the pointer, right, as we move forward. Now, if we are here, then we know that there is a previous, and we are at pointer. If pointer is at 300, where is the previous? Previous will be pointing to 200. So my previous next, which was this link, has to be broken and become equal to the pointer's next. Why? Because remember that we are trying to we have 300 which we are trying to remove, whose next is 400. So we are right now trying to do what? We are removing this link, we are deleting this record, right? So removing this link and moving this link here. So how do we get to this previous next? How do we get to this pointer next? So previous next is equal to pointer next, right? And if the previous is equal to the last, right, if the previous is equal to the last, then the last is equal to previous. Why? Because you have to take care of the fact that you are at the last node and your previous next is equal to pointer next, means that you are deleting a node which made you the last node. You are previous, right? So you are deleting pointer, but because you are deleting pointer, you are actually deleting the node which makes you the last node. So I have not discussed that case here. So let us say that that case is looking like this. You are deleting this. If you are deleting this, then you yourself, that is your previous next is equal to the pointer next. What is my pointer next? My pointer next is my pointer was pointing to this node, my previous next was pointing to this node. So this particular node which is previous, that next should point to wherever the last node was pointing. The last node was pointing here, so the previous next, that is here, should point to here, because we are deleting this. So either we are deleting something in the middle where we know what adjustments we had to make, we have to make this adjustment, or we are deleting at the end where we know that we have to remove this link which was going back to the front and make this go back to the front, and that's what we are doing here, right? So that's something that we are taking care of here. Now the other cases that we have left is if it is only the node. If it is the only node, if we are deleting only this node, there are no other nodes. Suppose this is the only node, right? There are no other nodes. Then if this is the last node, then all we need to do is we have to say my last is equal to null and free this, right? So my last was pointing here. Suppose this was 100, my last was pointing here. We are removing this, that means last should become null. So that's all we need to do. So case 1, which is only one node, is this. Case 2 is if you have at least one node, right? So if you have at least one node, then the situation will be like this. I have at least one node and this node points back to me. This node is at 100, right? And I want to delete this node, right? So if I want to delete this node, and of course this is not the only node, so I have, sorry, I drew it wrong. This is not the only node, right? We discussed the only node case just a few moments back. We are talking about a situation which is like this. right? And we want to delete this particular node. Then what will happen? Our last is pointing to 200, and we want to delete this node, right? So our last should change. Our last, whatever is pointing to 200, that particular next should point to itself. Last should still remain at 200, but that particular next should point to itself. And how do we get itself? This is our pointer. Our browser will take it, our browsing algorithm will take our pointer to point here, right? Which is our browsing algorithm? We have discussed that, right? This is the loop, this is the loop, this is the browsing algorithm. So when we actually enter a node, pointer has a value. That pointer value is after that particular value is supposed to be deleted. So it's deletion by value. The value was found at this pointer, so delete this. If we delete this, then our last next should be pointer next. Where is pointer? Pointer is at 100, because pointer stopped at 100 because that is the node which matched the value. So pointer's value was 100. So what is pointer's next? Pointer's next is 200, and we are saying put 200 here, self, right? So you can put that way. Last next is equal to pointer next. That is the way for actually adjusting the first node. So delete by value is something that you need to be cautious about, because this is a favorite question that is coming. So be careful if you want to actually score on this. 3 cases, please remember, and in these 3 cases, the first 2 cases are very simple. In fact, the last case is also very simple. As long as you know how to move your pointers, I think you should be good, right? Order of n, again it will be, as you can understand, because the value can be anywhere. Now traversal is easy. I don't think you need to worry about traversal. This is how we stop the loop, because this is a circular loop, it will go on forever. So what are we saying? Pointer is not equal to last arrow next. So we are saying pointer equal to last arrow next to start. Remember, we will not take the we will not play around with the last. We will store last next inside pointer, right? So that becomes, pointer becomes equal to the head, right? So and then we are saying that head, please go to next. Where? Here. Please go to next and start printing the data. So it goes up to next and starts printing the data. Till what time? Till the pointer becomes equal to last next. Last next is head. So till the pointer comes back to head again. Right? So pointer. So again, I have drawn this multiple times and drawing it one more time. So if this is 100, this is 200, this is 300, then my pointer is here at 100. It goes to next 200, goes to next 300, goes to next 100. At this point, what becomes? Pointer is equal to last next, because last was pointing to 300 whose next was pointing here. So last next is the same as pointer now, because last next is 100, pointer is also 100, and therefore it will stop. So that is how you do traversal. Order of complexity, you can understand, it will be an order of n. Searching an element, we have done it multiple times. Again, just take the value, take the head, and do this loop until you find the data, print the data, come out. After the loop, if you come out, because you are coming out at return, after the loop, if you come to this line, it means that it was not found, just like the earlier case. Order of complexity is order of n again. So that's pretty much what we had to cover. Questions that come: define circular linked list, double linked list. We have defined it. There is a difference that I have created. Feel free to understand this. Double linked list and single linked list, is the difference is on the 2 pointers, difference is on the traversal, difference is on the memory usage, difference is on the last node pointing to. See this question, we just now discussed this. So that's also done. Which type of linked list contains a pointer to the next as well as to the previous node in the sequence? a double linked list, right? So we know that. Next and previous. Disadvantages of a circular linked list. So the advantage is that we take the last and we actually do the insert at end or delete at end with order of 1 complexity. So the traversal can continue indefinitely. Any node can be the starting point of the traversal, right? So we can start from anywhere as a traversal, because we don't need to necessarily start from head, right? We can start from anywhere because I know that it will come back. And round robin scheduling, the processor time scheduling, all that is the use cases of basically this double linked list. And the disadvantages is, of course, that you don't know, sometimes you will get into a infinite loop situation because you are moving around. You don't know which position you are from the beginning, right? So you might be difficult in terms of debugging. Insertion deletions, you saw that it is a bit more complex than that of the single linked list, right? So that's the double linked list problem that we have. Sorry, the circular linked list problem that we had. And that's pretty much the main advantages and disadvantages that you need to talk about. Now this is what I was talking about. See, insert a node at a given after a given node in a double linked list. Let's draw the double linked list. So our double linked list will not take too many elements. We'll just try to figure out how many pointer exchanges. And that's what I was telling you, this particular kind of a problem will come. And let us do one more node, and then this becomes null. And we have this pointing to the previous node, and we have a head here which is pointing here. So that's our double linked list. So insertion a node after a given node in a double linked list requires how many pointer exchanges? So let us say we have to insert it after a given node, means we have to insert it after this. So our new node looks like this. So how many pointer exchanges we have to do? So first things first is, this particular pointer will now come here, right? So this particular pointer will come here, and this will we are talking about insertion, right? I thought we were talking about deletion, my bad. Let me go back. So we have this new node, we want to insert it after this node. So if you have to insert it after this node, this point is invalid. So this point has to come here, that is one pointer exchange, right? So this is one pointer exchange. Next, what needs to happen? This particular node needs to point back to this node, that is the second pointer exchange, right? And then what needs to happen? Then this previous node needs to point to this node. So for this particular node, the previous node is the new node, and for this node, the previous node is this node. This is the fourth pointer exchange. So these are the 4 pointer exchanges that we have to do, right? The best way to remember is that you are eliminating 2 here, so you will have to adjust 2, right? And of course, because your new node also has 2, you need 2 more. So that's the best way to remember it, right? So because you have to eliminate 2 pointers, adjust it, that means there is a pointer exchange going on. And because you have yourself 2 pointers, those 2 pointers would also need to be adjusted. Hence, we have a total of 4 pointers that need to be adjusted. So net, what it means is that this pointer needs to be adjusted, this pointer needs to be adjusted, this pointer needs to be adjusted, and this pointer needs to be adjusted. That's what it means. I hope you have understood, and I hope this is the last, I hope, yes. So I hope this circular linked list and double linked list is clear. We'll meet in the next class, which will be on trees. We start trees in the next class. So watch out for that lecture. Thank you so much.